the West Atlantic ice sheet and the Greenland ice sheet contribution to sea level rise. Current estimates show that global sea level rise would rise by more than 3 metres at an unknown rate. A simplified analysis suggests that much of the ice sheets will survive beyond this century. The marine isotope stage 5 shows that warming is to a greater extent more significant in the Holocene. The pattern of MIS 5e sea level rise indicators provide a 95% probability that the Greenland and Antarctic ice sheets each contribute at least 2.5 metres of sea level rise to the maximum of approximately 6.6 metres above modern levels, with a 67% probability that it exceeded 8 metres. Forcing by atmospheric or ocean warming could produce large future contributions of the West Antarctic ice sheet to sea level rise. Ice sheet simulations suggest that the loss of large ice shelves by atmospheric or ocean forcing would probably presage collapse of the bulk of the marine ice sheet and West Antarctic ice sheet. The Northern Hemisphere sea level is affected to a greater extent by the collapse of the West Antarctic ice sheet than the Greenland ice sheet due to compensating gravitational effects on local sea level when ice is lost from the latter. Currently, West Antarctic ice sheets contribute to sea level rise of between 0.5 metres and 5 metres a century at a normal rate. In worst case scenario, this gives an approximately 6 metres rise of global mean sea level rise from 2030 to 2130. Furthermore, an estimated that roughly 400 million people, 8% of the population, are threatened by a 5 metre rise in sea level. This 5 metre rise of sea level would have impacts that extend beyond the coastal zone and alter the coast in a dramatic manner. As soon as sea level rise from the West Antarctic ice sheet melting accelerates in 2030, the length of the world's coastline that is protected declines from about 85% to 50%. The threshold of sea level rise to trigger higher protection costs is exceeded at the same time for all West Antarctic ice sheet collapses scenarios, except for the slowest scenario in which a collapse takes 1,000 years. If West Antarctic ice sheet collapse occurs within 100 years, land loss would increase eightfold. When West Antarctic ice sheet collapse ceases, the length of coastline that becomes feasible to protect is a fraction of what it was before the West Antarctic ice sheet collapsed. Together, the Greenland ice sheet and the West Antarctic ice sheet hold enough cubic metres of water to cause sea level rise of around 12 metres. The Copenhagen diagnosis report shows that the global average of sea level rise to be 80% above the IPCC's predictions. This acceleration in sea level rise is consistent with a doubling contribution from the melting of glaciers, ice caps, Greenland ice sheet and the West Antarctic ice sheet.
The first approach is numerical models with different emission scenario inputs. Formulas and calculations are used to produce different outcomes depending on what the environmental inputs are. The second approach is semi-empirical. These are observed relationships between sea level change and global temperature change, but these do not consider individual contributions and their constraints. The second uncertainty is cryospheric contributions. These can't be calculated to a sufficient extent. There is a much greater reliance on observations to try to predict future changes. Smaller aspects of the cryosphere, so excluding the Greenland and Antarctic ice sheets, can't be fully accounted for. For example, the quantity of water from permafrost melting that will reach the seas is unknown.
Finally, assumptions made about demographic, social, economic, technological, and environmental developments as inputs into models can vary, making some predictions incomparable. Some of these include whether there will be high or low economic growth, high or low population growth in the future, efficient or inefficient technology, innovation and development. So for example, will they be clean technologies and sort of clean fuels, or slow and more diverse? And also the use of fossil fuels, will they stay intensive and high over the future? Will they become more balanced, or will we try to cut them out as much as possible and become more limited? The first mechanism of sea level rise is through cryospheric melting. One way this can happen is through calving from tidewater glaciers that can directly contribute to sea level rise. Land ice melt has grown from being around 55% of overall contribution of sea level rise from 1993 to 2007 to 80% from 2004 to 2009. The second mechanism is through steric changes. This is ocean water density changes. One component of this is thermosteric changes. Thermal expansion has accounted for 55 to 69% of sea level rise in 2100 relative to 2000. The third mechanism is through glacial and ice sheet melting as primary contributors. So the Greenland and Antarctic ice sheets and glaciers are the biggest suppliers of meltwater. Meyer et al. Estimated that land ice loss from the Greenland and Antarctic ice sheets, aggregate glaciers and ice caps would contribute to around 8 to 16 centimetres of sea level rise by 2050 and 17 to 56 centimetres by 2100 under realistic future conditions.
The original SMPs divide the UK into 11 coastal cells. By using this method, it assumes that the whole area within each cell will react to coastal erosion and sea level rise in the same way. In the case of the Yorkshire coast, the geology is not consistent with the entire cell. In the northern region, this consists of rock produced in the Jurassic period, such as sandstones. These are durable and hard and can withstand coastal wave action. However, it's susceptible to acid dissolution associated with climate change and acidification. Therefore, currently these can withstand oceanic conditions, however in the future this can lead to greater coastal erosion. On the other hand, the southern region is covered in Cretaceous rocks such as chalk and boulder clay. Chalk-based rocks are very porous and can cause cracks in the drainage system within the rock structure. This suggests other climatic factors such as precipitation play a role in this coastal erosion. Boulder clay is easily eroded when saturated, which means the increase in sea level rise poses greater threats to coastal erosion. As the SMP requires one of 4 action methods to be implemented along the entire coastal cell, these methods may not provide any use, as altering geology means different strategies must be implemented across the coastal line to effectively reduce the effect of sea level rise and reduce the chance of flood. Another issue is that they assume the coastal sea level rise. Within the first SMP, the recommendations did not allow for sea level rise associated with climate change. Instead, they assumed a 5-metre high level rise mark, but did not provide an estimate to when this would happen, to allow for management strategies to be implemented in time. With the initial lack of scientific evidence for how the coast will react to sea level change, the methods used to prevent coastal erosion are not suitable for the future, therefore only providing a short-term management strategy for current climatic conditions. There is evidence of greater flood risk associated with the Western Antarctic ice sheet melt, which may equate to a 6-metre rise by 2130. The first SMPs may not be suitable in the future, and so another strategy will be required to be put in place to resolve these assumptions of minimum ocean level rise, or even the 6-metre extreme sea level rise. As a result of this, using scientific knowledge and accurate evidence allows for better understanding of the areas affected and what coastal defences will provide suitable. In addition to this, more understanding of the effect of sea level rise allows for greater potential for governmental and external funding into protecting the Yorkshire coast. Therefore, by assuming the coastal sea level rise without scientific evidence, further risks are expected. The final assumption is that protecting urban areas will reduce the effect of coastal flooding and erosion on humans. This completely ignores the effect of down-coast erosion due to lack of protection. Understandably, the cost of protecting the whole coast is an expense, and the Yorkshire Government website stated no further or external strategies or investment can be used unless actively put forward by the government. However, by introducing and promoting external companies to invest, this will lead to benefits in maintaining the coast and reducing the development of new issues in the future. In addition, these policies are limited to locations where evidence exists that social, economic and environmental benefits of defences would outweigh the possible negative impacts for wider coastlines. However, in studies it is stated that the government should look at future projections surrounding economics, environmental and social factors to observe how the coastal system will change and implement policies this way, rather than focusing on current events. In addition, it is recommended to allow external agencies to implement research, provide financial and technical assistance, as this will provide greater understanding between the coast and adaptations to global climate change. When looking at the maps, only protecting urban areas will provide increasing risk of future flooding. When looking at the areas near the Humber, even with a 2-metre sea level rise without mitigating any defences, areas further inland are at risk of flooding as tidal water backs up the river. Therefore, in areas with rivers and the ability for the ocean to back up onto the land, defences must be constructed even if there are no current economic, social and environmental benefits. As a result, they cannot assume current socio-economic and environmental impacts will be beneficial to future projections and must consider looking further.
In an area that has some of the highest erosion rates in Europe, it is only inevitable that the rising sea level will have a significant impact on the Yorkshire coast. At Albury, a village on the Holderness coast, erosion rates are estimated at 1.5 metres per year. With the sea level rise being linked to changing erosion rates, the severity of sea level rise over the next century will impact communities such as Albury along the Yorkshire coast. Increasing erosion rates will not only put stress on the coast, but also on the current defences and any future defences built to protect the communities on Yorkshire's coasts. The extent to which flood defences such as the barrier on the River Hull are successful at protecting the areas from coastal flooding in the future is dependent on the severity of sea level rise. Sea level rise itself will also affect communities along the Yorkshire coast. It has been predicted that a 1 metre sea level rise will put a significant number of properties at risk on the Yorkshire coast, including hundreds on the Holderness coast and thousands on the banks of the Humber estuary, where more popular settlements such as Hull, Rimsey and Cleethorpes are located. The Humber estuary is economically important for both Yorkshire and the whole country, with ports at Hull, New Holland and Grimsby and Immingham, the UK's busiest cargo port. The risk posed to ports on the Humber is already clear. Immingham, for example, was affected by flooding in December 2013. The Government Office for Science report in 2017 states that UK ports will be significantly impacted by a half a metre sea level rise by 2080. The Humber Estuary is also the location of multiple power plants such as the gas power stations at Immingham and Saltend. If future coastal flooding was to affect these power stations, this will put a strain on power supplies in the region. The region's vulnerability to rising sea level will need to be considered in future power stations and the defence of protecting current ones.